Have you ever heard about this game Asteroids? It's super stressful and it looks very old. It actually is very old. I think your parents played this game already on a machine like this one. It was released in 1979 and well, it was one of the very early games in the history of gaming. And eventually also became the best-selling arcade game of all time. That's pretty impressive. Now, you're probably asking yourself why we're playing old games with poor computer graphics in half video. Well, I'm getting to it in a second. So what I want you to do is, I want you to change perspective. So I want you to look at this not from the perspective of a player, but actually from the perspective of a developer. So I want you to ask yourself, how could I develop a game like this? And what kind of mathematics do I need? Now, probably would be a good time to quickly pause the video and think about this question. And you will see, the answer is actually surprisingly simple. So there's no rocket science involved or anything, and by now you have actually heard about many of the concepts required. So let's dive into it and break it apart. We're going to start with a blank black space. Next, we place our spaceship on the map. Now, the question is, where should we put it? As game developers, we need to define the position of the spaceship in our code. Now, that's the point where we start entering the world of mathematics. We can easily achieve this by laying a coordinate system over our map. The position of our spaceship is then defined through a position vector pointing from the origin to its position on the map. And we can then place more objects on the map, like these asteroids here. The asteroid's position, however, is not static. Rather, the asteroid is moving along a certain line at a certain speed, here highlighted in red. Same holds true for our third and last object, the shots of the spaceship. Also, they are not static and move along a certain line at a certain speed. So in a nutshell, the two core elements of our game are objects, here highlighted in purple, and movement of these objects, here highlighted in red. Now I want you to quickly think about and ask yourself, is this really different in modern games? The answer is no, not really, right? Sure, we have all the fancy graphics because today's computers are so powerful that they can render beautiful worlds. But the underlying principles are the same. We have objects that move around. A very important mathematical concept to describe both objects as well as movement of the objects are lines. Now, computer graphics are essentially just a bunch of lines and planes. And also modern computer graphics, they appear very smooth and everything, but that's just because their surface has been approximated by millions of tiny little triangles, where each triangle is bounded by 3 lines. And also the movement that we identified in our asteroid game was along lines. So, because lines are so crucial both for describing objects as well as movement of objects, we are now going to take a closer look at lines, and the goal is to describe lines from a mathematical point of view. Actually, you already learned about ways how you can describe lines mathematically. So let's have a look, for instance, at this green line here along which the shots of the spaceship are moving. Take a quick moment, pause the video and think whether you would be able to describe this line mathematically. Well, the equation of the line reads y equals mx plus b. And m and b, they have a meaning attached to it. So b is the y-intercept, in this case it's 1, and m is the slope of the line, which is defined as rise over run. In this case it's 1 over 2. And it tells you that if you go 1 unit to the right, you move up by 1/2. So, in summary, the equation of the line reads y equals 1/2 x plus 1. Or, if we move all the variables to one side, minus 1/2 x plus y equals 1. Now, this would be a linear equation with 2 variables. Now you may say, okay, that was in the 2-dimensional space, But what if we are in the three-dimensional space? And besides, all we know now is that the shots are on the green line, but we are not really able to describe their position on the line with respect to time. So there are still some limitations. Let's first try to see if we can extend this concept into the three-dimensional space. In the two-dimensional space, our line can be described by the linear equation ax plus by equals c. In our case, a was minus 1/2, b was 1, and c was 1. So let's be naive for a second, and I encourage you to take a curious, naive mindset as often as possible. That's the best way how to gain new insights in mathematics. So naively, we might see a pattern here. What if we just add the third variable z into our linear equation, so that it reads ax plus by plus cz equals d. This could give us a line, right? So let's try it out. And we keep it simple for this. Let's just say our parameters a, b, c, and d are all 1. So we are looking at the equation x plus y plus z equals 1. And we can use Geogebra to visualize this equation. I encourage you to pause the video and try this on your own. The link is in the video description. Alright, let's put our equation into Geogebra. First we need to make sure that we are using the 3D calculator here. And now we can just plug it in with x plus y plus z equals 1. And what we get is a plane. This doesn't look like a line, but we actually get a plane. So our naive approach, well, it was a good idea, but it turned out to be wrong. So the question we are going to explore over the course of the next lessons is there another way how to describe lines mathematically than the one you already know? Maybe one that is better suited for our purpose? And the answer to this question is yes, there is. So get ready to dive into it. It's going to be very exciting and I'm sure you're going to love it.